Let's look at another interesting subtopic in chemical kinetics, and this is the final subtopic in chemical kinetics. So let's start with a reaction mechanism. So a reaction mechanism is the step-by-step sequence of elementary reactions by which an overall reaction occurs. The key idea you should know is overall reaction is not a single step, but it is made up of what? Of several elementary steps. So let's look at an example, an application example. For example, this reaction does not occur in one step. It occurs via what? Intermediate species. Now, let's having talked of step or like sequence of elementary reactions, let's talk about elementary steps. What is this elementary step? So an elementary step is a reaction that occurs in one molecular event. In an elementary step, the rate law can be written directly from the equation. The coefficients are the reaction orders. Now, there are types of elementary steps. So these are the types of elementary steps: unimolecular, bimolecular, demolecular. So for example, uni, it means one. For example, the one reactant is equal to products. Bimolecular, two reactants are reacting to produce products. Demolecular, there are three of them. So having talked of this, now we can connect to the first definition which we said a reaction mechanism is a step-by-step sequence of elementary reactions by which an overall chemical reaction occurs. So these are the elementary steps that we talked about. And the molecular steps are rare because they are unstable collisions. Now let's talk about the reaction intermediates. Reaction intermediate is a species that is formed in one step and is consumed in a later step. So it does not appear in the overall reaction. What we mean is, for example, we have this example: NO2 plus F2 is equal to NO2 F plus F. Then there's going to be another reaction which is going to be NO2 plus F is equal to NO2F. So an intermediate, when you look at this one, the first reaction, NO2 reacted with F2 to produce NO2F plus F. But again, the second reaction that comes, this F, here it was a product, but here it's going to react. It's going to be a reactant to produce a product. So this F is the one we call an intermediate. That was the example, NO2 plus F2. As you can see, it was a product but now it's a it's a reactant. So it's formed in one step and later consumed in in another step. So F is is the intermediate, a reaction intermediate. Let's talk about another interesting and important subtopic. So the rate determining step. So the rate determining step is the slowest step in a reaction mechanism and controls the overall reaction rate. So the rate the determining step is the step that is controlling the overall reaction rate, and it is the slowest step in a reaction mechanism. So the key rule is the rate law is determined by the rate determining step. So you should know the steps in identifying the rate determining step. The first step is you should find the slow step, and the second step is write the rate law from the rate determining step. So we are going to have an example. So just as I said, step 1 determine the identify identify the rate determining step. And the rate determining step, so the slow step is step 1. Oh, not step 1, but reaction 1, which was slow, NO2 plus F2. Then step 2, write the rate law. So what is the rate law? As we learned in the previous video, how to write the rate law. So the rate law, we just write the the reactants. We consider the reactants. So the rate law is going to be K NO2. Then, as I said, the coefficients are the reaction orders. Since the coefficients here, it's 1 and 1, so we don't raise to any power. So it's KNO2, then F2. So this is the rate law. KNO2, then F2. Rate law for chemical kinetics, or we consider the reactants. That's what you should know. So there we go. That's the rate law. So another complicated example. This is another complicated example. So for this one, we get the rate law from the slow step, and the rate law from the slow step is going to be K N2O4 CO. So this is the rate law from the slow step. Now, step 2, let's remove the intermediate. What's the intermediate? N2O4 is the intermediate. It's appearing in both sides. It was the product here, and it has become the the reactant here. So let's remove it. Now, how are we going to remove it? We know that N2O4 from the first step is equal to K. We are going to put the inverse NO2 squared. Why are we putting the squared? Because there were two of them here, which were equal to N2O4. Then therefore, after doing this, we are going to get where there is this, we are going to put what? K inverse NO2. So let's go ahead and do that. We are going to have the rate is going to be K. Since the K's are going to be 2, the one we got from the K inverse of NO2, so we are going to put that one there. Then we put NO2 squared, then CO. So don't be confused. We just replace, because the rate law. So don't be confused. We just replaced where there was N2O4. We replaced this, because from this reaction, this is equal to the two of them, because they are the same. That's why we have put NO2 squared and put the inverse. Because the K will be two of them. So that will be the rate law for that reaction. So our aim was, at first we just wrote the rate law for the slow step, then we remove the intermediate. Always remove the intermediate from the reaction. So let's talk about a catalyst, which is the final concept in this subtopic. So a catalyst is a substance that increases reaction rate and is not consumed. So it increases the reaction rate, but it is not consumed. Then also it provides an alternative pathway with lower activation energy. So that's where we are going to say catalyst lowers activation energy, but reactants and products remain unchanged. So for example, an example is this reaction that I've written is hydrogen peroxide, 2H2O2, that's hydrogen peroxide, decomposes slowly at room temperature when manganese oxide is added. So manganese oxide is not there in the reaction, so that's the catalyst. The reaction becomes rapid. So manganese hydrogen peroxide has decomposed to water and oxygen. Now, manganese oxide acts as a catalyst and it provides an alternative reaction pathway, and it also lowers the activation energy and increase rate without being consumed. Now talking of activation energy. So activation energy is just the energy which is required to initiate a reaction. For a reaction to start, there should be energy which should make that reaction start. That's activation energy. Now catalyst lowers that amount of energy which is needed to start or to initiate a reaction. So exam tips about this topic is: rate law comes from slow step, and always eliminate intermediates. Do not guess mechanisms, and use a clear chemical reasoning. So what's the summary? The summary is just that reactions occur in steps, and the slowest step controls the rate. Mechanisms explain rate laws. Catalyst lowers what? Activation energy. So this is the end of the topic on reaction mechanisms. Maybe in the next lesson we'll talk about diagrams of this activation energy, when energy is doing what and what. That's what we'll talk about. So thank you for watching, and don't forget to subscribe if you haven't subscribed yet for more lesson videos.